Now that we have done a little bit more of the counting principles, we go back to what chapter 8 is actually called advanced counting techniques. And they are advanced because they use techniques such as recurrence and so on. So we're going back to recurrence relations again. And I remind you, a recurrence relation or function defined by recurrence is a function that's defined whose value at a particular n is defined by its values at lower values. Okay, so that you kind of build up the function as you go along. So, and we have seen a particular example of this, the Fibonacci sequence. So, Fibonacci, I always have to think it's the double C. It's the Fibonacci, and in fact, Fibonacci came up with this thing because there was a problem that was posed in his book. In a book that he wrote in the 13th century, in the book called The Book of Counting, Liber Abaci, he posed the following problem. He says, okay, suppose we are on an island and we have rabbits, and we put a pair of rabbits, a male and a female, okay? And so we have, we start with one pair. So whenever I say a pair, I always will mean a female and a male, okay? We have one pair of rabbits. Now, any pair after 2 months produces another pair. I mean, you know what they say about rabbits, right? They do it like rabbits. It means they do it pretty much. After 2 months, they produces another pair. So any pair, because at some point there are more and more pairs, any pair after 2 months produces another pair every month. So the first, in other words, it takes 2 months for them to be mature, and then after that, every month they produce another pair. Now, this is on a huge big island. In fact, things like this kind of happened in Australia. They introduced some of animals. I don't know exactly what it was, rabbits. It was some animal that was had no predators there, and it was a huge place. So they really grew a lot, the population there. And we're going to assume for simplicity, well, that's kind of a big assumption, is that they don't die, okay? And they're all fertile, and they all do this. They have this. So let's count. The question was how many pairs are on this island after n months. Okay, so let's make a little table here. So here is the number of months after the after 1 month. How many pairs? The number of pairs. We have one pair because that's what it started. In the second month, we also still have one pair because nothing has happened. But in the third month, this one pair introduces a new pair. So, okay, now we're going to have to make, in order to count this well, we have to call here the number of mature pairs. And here the number of immature pairs. Because the problem is that this delay of 2 months, right? So this column here will be the sum of the next two columns. So let me therefore, perhaps in another color here, originally we have 0 mature pairs and 1 immature. Immature means it cannot produce yet, right? And same in the next month. But in month 3, our first pair becomes mature, and it produces another pair, which of course is immature. Okay, so at this point we have 2 pairs. Okay, let's see what happens now. How many mature pairs do we have next month? Well, the mature pair of course stays mature, but the immature pair is not maturing yet, so we have only 1 mature pair. How many immature pairs do we have? Well, we're going to have 2 because our original pair has produced another one. Okay, so and now we see that after 4 months, so let's make it 5, 6, 7. I think by that time we'll figure out what is going on. We have 3 pairs. Okay, so now the next month, again, what happens? Well, one of these immature pairs is now matured, so we're going to have two mature pairs, each of which produces an immature pair, okay? And that's it. Wait, now wait, no, wait, what I'm saying. Yeah, right, sorry. Okay, sorry. So these two pairs, what happens to them? One will go there and one will stay there, okay? And then this pair, together with this, one of these pairs, these two here will create two immature pairs. So it's 2 plus 1 here, okay? So I repeat, what is happening? We have two immature pairs. One, we should perhaps, yeah, it would have been better perhaps even to make a third column to keep track of that, but okay, let's do it this way. So of these two, one is now becoming mature, so that moves into here, okay, and one moves into here. Now the mature pairs, which do produce two offsprings. Okay, that's the situation at this stage. So we see that at this stage we have 5. Okay, let's analyze what happens in the next stage, and then hopefully we will figure it out. At this stage, let's see, how many are matured now? Well, this guy here has now matured, right? Because remember, it was produced 2 months ago. So this one will now also move into there. So instead of these two, and of course these two remain there, so we'll have 3 here. And these two guys, well, okay, sorry. So we have 3 mature pairs. Each of these 3 produce 3 new offsprings. And then we have the immature pair, the 2 immature pairs that we have here, that were freshly created, so to speak. So they go here, okay? So we have plus 2 here. So what is the number that we have here? Well, it's 8, okay? Now, if you remember the Fibonacci sequence, if you look at this first black column here, these are the Fibonacci numbers, right? Let's do one more time. Let's see whether this match up. The next one should be 13 then, right? If these are the Fibonacci numbers, remember the Fibonacci numbers are obtained by adding the 2 consecutive and add them up. So we add them here. So you add them. How do you do this? Let me do this. So you take these 2 and then you add them and you get this number, right? So there should be 13. Okay, let's see. What do we have? Well, how many mature pairs do we have? Let's think about it. These 3 mature pairs remain mature. So there's definitely 3 here. These 2 have had the time to mature, so we get another 2. So we get 5 pairs here. What about the remaining? Oh, okay, and those 5 pairs create 5 new pairs, right? Because they're all matured, so they can produce. So we have 5 here. Now what happens to the other 3 that we have here? Sorry, this should have been, yeah, my colors are a little bit off here. I don't know, my colors are no, I'm not doing my colors very well. Let's not worry too much about color. What about these 3 here? They were only 1 month old, so they are still immature, so they come here. But they will be matured next time. So I was making those red, I guess. No, my color scheme is completely off. But the point is, my number is correct, right? Because look, this is 10 plus 3, that's 13. Okay, so it is indeed the Fibonacci sequence that we get. Okay, so so we can perhaps try to write this now down and show this. So remember, repeat, the Fibonacci sequence. So Fn is the number of pairs. Notice that F1 is 1, F2 is 1. F0 is 0, but okay, that we know, right? And now we have the number of pairs is given by the relation. We basically have the number of mature pairs from the previous time, Fn minus 1, plus the number of immature pairs from the previous time. That's how it works. Okay? Now, I'm not proving this, I agree. And that we can do by induction. So if we would prove that this is exactly the formula, we would use induction. But I don't want to do this now. I just want to show you how these things can be used to model, recursive relations can be modeled to counting problems. Here's another one. It's a very famous one, the Tower of Hanoi. And it's there's a legend, a story that goes with it. I mean, I don't know whether it's a made-up story or not, but and it says in a remote monastery in the Tibetan mountains in the Himalaya are monks trained specifically for this one purpose, and they play the so-called Tower of Hanoi game. So what it is I'm going to have to make it a little bit sketch. The sketch in the book is a little bit better, but okay. So we have 3 piles. And in these piles, we put wheels of increasing bigger size. Okay, and we put the biggest one on the bottom. So the biggest one would be here, say. I'm going to only do 4 here, because, and then the next biggest one would be there. And then this would be the 3rd biggest one, and this would be the smallest one. So this would be, n is going to be the number of tiles, pegs, whatever you call it. So n is the number of tiles, and in this case, n is 4 in my example. Okay, and what did the monks have to do? They have very simple thing. They have to just move this pile onto this peg. Okay, they have to go from peg 1 to peg 2. Let's call this 1, 2, and 3. Okay. Well, that would be easy, right? Except they can never put a bigger one on a smaller one. Okay. Let's say that is just somehow the rule. You can never put, so never bigger on top of a smaller. That's the only restriction that you have when you move, and you can only move one at a time. Okay. So the original story was then this. There were, so in the legend or story, let's call it a story, right? N was 64. There were 64 pegs. Not huge. It was a big pile, but okay, 64. A couple of good, well-fed monks, they can do this, right? And so they were told, okay, you have to do this fast, okay? Every second you have to move. So every second, move a tile. Okay, and of course, I mean, they take turns, right? They go eat and sleep, and then perhaps even do other stuff we will talk about later. But they do this every second. They move a tile, and now the prediction is, once they have finished their job, the world will end. Da-da-da-da. Now that sounds bad, right? So the question is, how long will it take them? So when will the world end? If this is true, if this is a prediction in a la Nostradamus or something like that, so how long will we still have to live if they start doing this, say, now? Okay, or they did it perhaps 10 years ago? We don't know. Let's see. Let's figure this out. Now, what I'm going to do is I'm going to try to find a solution for you for n equals 4. Now, I'm going to go draw my back again. And also, since I'm going to have to start erasing things and so, I'm going to just draw my pegs as single lines. My tiles as single lines, okay? I have to make sure that I have 4 different sizes. Okay. So, and here is the number of moves. I'm just going to tally them. Okay, my first move, what can I do? Well, I have not much choice, right? I have to put this guy somewhere on one of these pegs. Now, I must admit, I'm going to do this kind of blindly, and I might end up with a pile, not on the second one, but on the third one. Let's say, as long as I've moved my pile, I'm fine, okay? That really doesn't make a difference in the number of moves. You just have to be more clever, but I'm not that clever yet, so I'm just going to do it. Okay, so I have only one choice. This has to go to one of these 2, so let's do that. Okay, so after one move, I'm going to put say, this guy here. So this is now gone. I hope this goes without losing. I lose my middle peg. Okay, this is going to be cumbersome. So I'm going to actually make okay, so this is gone, right? So I shouldn't draw it anymore. Okay, so, okay, guys, I didn't test it out beforehand with my, so I'm going to do a little bit. I'm going to, so where are we? Sorry, no, this is, sorry, no, okay. Let's not put, I'm not going to put the bottom line here, that makes it too confusing, okay? So I'm just going to put this, and also I'm going to put my pegs, sorry, let me set this up, because the way that my pencil works, my pen works, So here's my one pile. I'm going to only put them on one side. Okay. So these are the three biggest ones, and I put the smaller one here. Okay. That's one move. What's the next move? Well, now I can do, well, a stupid move would be to move this one around. What am I going to do with that? So let's not do that. So I'm going to move this one, but I have now only one choice. I cannot put it on here, so I have to move it there. Okay. So after the second move, I'm going to move this guy over there. So it comes here. Okay. We hopefully I'll keep the sizes. Okay. Now the next move. I'm a bit stuck, right? If I want to move, I'm trying to move all these, of course, but I cannot move this guy because both of these would be smaller than it. So I have to make first space, and the only space I can make is by moving that over there. Okay, got it? Okay, so doing that one there. So it becomes now here, and that was another move. Okay. Now I can move this guy. Okay, I'm going to put it here. All right, so I get it here, and this is now gone. Great. Oh, did I? Oh my God, did I move this? No, I didn't count it yet. Oh no, sorry, I didn't count it yet, right? Okay. So my next move is, well, I want to get rid of the last biggest one, but I cannot do this anything. So I have to start moving. I want to move this guy on top of here. That would be great, right? Because then at least that's already that. Then I have a spot. I have to free a spot for this guy. And I cannot free a spot by moving this one around because this is too big. These two has to go on top of here. Of course, I can put these two, try to put it on top of there, but then I'm blocking this one. So the best move would be to move these. Now, if I move the small one and put it on top of here, what am I going to do with the second smallest one? So actually, if I want to be smart, I'm going to put this smaller one up there. So I'm finding the optimal strategy. There are worse strategies. Of course, you could start moving one tile from one to the other end without doing anything else. Okay, so we do this as optimal as possible. So okay, what I'm doing is, so my next move, let's count it first before I get it. I'm going to put the smallest one on top of my biggest one. Okay, so this is now gone. Ooh, not the whole thing, only this. Okay, all right. So now I can move this second smallest one on top of here. So that's another move. Okay, one move. I move it here. So this is now gone. Good. Okay. I want to keep this spot free. Oh, what did I do? I want to keep this spot free, so I'm going to move my smallest one on top of this one. That's smart, right? Okay, so that's what I do. So again, another move. Let's count the move first before I do it. So here goes my smallest one, and here this is gone. Yeah. I have to put them a little bit, draw them a bit further apart, I think. Okay, so now I'm ready to move my next move, to move this big one over here. Okay, so this is now gone. Good. So I'm thinking probably I will end up with a pile in this pack. As I said, I was not smart. I didn't think properly here, but that's not the case. Let's not worry about that. The whole point is to move it. Okay, so now actually, if you now think a little bit, at which stage am I now? Look, I have to now move a 3 pile of size 3 on top somewhere. I'm moving this one. Where I'm going to move it is on top of this one. But it is a problem of the same Hanoi problem, but now with a 3 guy. And so that's the recursion here. Okay. However, I moved this. Remember, these 3 were originally here, right? However, I got these 3 there. I'm going to use the same strategy to get these 3 there, and then I'm done. Okay. I hope this is now clear. So you could kind of guess how many moves that is, but let me quickly try to do it. I'm probably going to lost my count somewhere. I should end up with the number 15, and I feel that I might end up with. No, let's see what we do. Okay, what we do? We have to move the small one. I'm going to move. Yeah, now we have to be a little bit more clever. I think I'm going to put the small one, the smallest one here. So this is gonna. So I'm going to put them a little bit, okay. Then I'm going to, so that's one move. I'm going to move the second, this market one, I'm going to move this here, right? So now this is gone. And then I'm going to use my, the next thing I'm going to do is put this guy here, right? So, okay, all right, so, So this one, I'm going to put it way high here that I don't erase myself. Okay, now I'm ready to put the second biggest one. This is, I forgot to count again. The next move is to move this guy on top of here. That's a good move, that's for sure. So my next move, I'm putting it, no, yeah, I'm not going to erase it anymore, so I can put it close. Okay, so this is gone. And now, okay, again, you see it comes down to moving a 2 stack on top of, to move this 2 stack, and where to move it to here. Okay, but that's very quickly done. Okay, so one more move to move the little guy away. Then one more, one more move to move this guy here. I think I miscounted somewhere. I think I forgot to count one. Okay, it's, sorry. This one is now my move, the move. I think I just double check it. We'll figure it out later. And so then the final move would be this. That would be my final move, right? Would be moving that one. And there I am. So 15 moves. So let's try to now analyze this and what actually is the number of moves that we do. And I already in the middle, when we were doing it, we found the strategy. So what we do is the following. Let's think about it a little bit more. So we have this pile here. I'm going to now make the pile look like something like that, right? And what I'm doing is I'm saying, okay, forget about the bottom tile here. So this is a pile. The total size of this pile is n tiles. I'm going to move the, and so this part here, let me call it the, I'll shade it green. So the green part here, that has size n-1, right? That's a pile of size n-1. I'm going to move that pile. So okay, let's set up the thing. H of n is the number of moves. So to move that green pile, how many moves do I have? H of n-1 moves, right? And I move this green pile to, say, here. So I'll make it here. It's going to go here now. So here's my green pile of n-1. Okay, so the green pile is now gone. I'm afraid that if I'm going to start erasing things, it's going to have to do it. Okay, so the green pile is gone. So the situation now here is, okay, is this. Okay, there's one disk left here. Okay, I'm moving this disk here. Sorry, okay, sorry about that. Let's move it a little bit better, a little more symmetric. Okay, here. So I'm moving this big disk here. You're following? Okay, so that's another move that I'm doing. So now this disk is empty too. And my claim is now, what I want to do, of course, it's obvious what I want to do. I want to move this guy on top of here and I'm done. And I'm claiming that I can use the same strategy as for the n-1 game. You say, yeah, but that's obvious. No, because there's a slight difference, right? There's now one tile here. One of the packs is not free. In the previous situation, when I started, I had 2 free packs. Here I have only 1 free pack, but actually the pack is free. Because what makes it not free is if I would put something on here that would be bigger. But there is nothing bigger. All these things are smaller. So as far as moving this is concerned, whether there's a pack or not, it makes no difference. So it's again the same strategy to move those n-1 on top of here, and so we get, so that again n-1 moves. So this is our formula. So the recursive formula is rather quick, right? This is our recursive formula. Now, of course, there is also an initial condition always, right? Recursion relations are initial conditions. In this case, how much does it take to move a tower of length of size 1? Well, 1 move. Okay, H1 is 1. So we could try to find a formula, and we will in next chapter. So this is part of this sections in this part of the. We're going to spend quite some time on this, a few weeks. We will see methods of finding solutions of this, but here we're going to do it what's called by hand, manually. It's called, the official title is iterative. Okay, so what does it mean is, okay, I'm going to just go down and say hn is 2 times hn-1 plus 1, and now apply the same recursion relation to the hn-1. So, and what is hn-1? Well, it is the same recursion relation, except instead of n, I have now n-1. So if this is n-1, this will become n-2, right? Okay, so we have 2hn-2 plus 1. Okay, let's work this out. It is 2 squared. I know it's 4, but trust me, it's better to write it that way. h minus 2 plus 2 plus 1, right? Expanding this 2 there. Now we say, okay, 2 plus 1 is 3. See, this is the thing with recursive solving iterative. You don't want to work out the numbers too quickly, because then the pattern is kind of lost on you. You'll see what I mean with that if I do the next step. Oh. So the next step is, I have to now replace this hn minus 2 using this formula. In other words, if this is n minus 2, this will become n minus 3 now, right? Because always one less. Okay, so we have 2 squared. Then there comes the new expression, and is 2hn minus 3 plus 1. And then I have the plus 2 and the plus 1 that I don't mess with yet. Why? You see now. Look, if I expand this, I get 2 squared times 2, that's 2 to the power 3, hn minus 3, plus 2 squared, plus 2, plus 1. Let's do one more step. So 2 to the third. Now, stop the movie, try to figure it out yourself. So here would go 2hn minus 4 plus 1, right? 1 less, plus 2 squared plus 2 plus 1, that stays the same. If I expand, I get 2 to the power 3 times 2, that's 2 to the 4, hn minus 4, plus 2 to the third, plus 2 squared, plus 2 plus 1. So what we get here, and that is important, is we see that we get an increasing number, on the tail part here are powers of 2, the sum of powers of 2. So when does this end? Okay, well, this will end when n minus 4 has become 1, right? If I keep going there, if this is 1, then this will end. So then is the question, what are at that point? This is perhaps the hardest part to figure out. So I keep going here until I do this how many times? Well, you can try to calculate how many times it is, but I want to do this when my index has dropped down to 1, because h1 I know what that is. Okay, so let's see what are the numbers then, the other numbers. Well, the first pattern that you recognize is that this 4 is the same as this 4. Okay, how does this help me? Well, I have to write here as a certain power of 2. What it tells you, another way perhaps to say that, even better way to say that, is if I add this exponent to this index, I get n each time. See, that's the pattern that where is it here? That's the pattern that I recognize. Even in the first time, right? This is power 1, and this is 1 plus n minus 1 is n. Okay, so 4, n minus 4 is n. So 1 plus what gives me n? Well, n minus 1 here, right? Plus. And what are then the other powers that I'm left with? Well, look, they are just, they start being, this one is 1 lower than this one. And this is 1 more lower, and this 1 more lower. So if I would write this up, this would be 2 to the 1 lower would be 2 minus 2, 2n minus 3. Plus, and how far do I go? Well, I still end up with 2n plus 1, right? Okay, we're almost there, because h1, this guy, I know what it is. That's what we need an initial condition. h1 was 1. Okay, so what we get here is 2n minus 1 plus 2n minus 2 plus dot 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 plus 2 plus 1. Now, this was a formula that we saw before. Go look up the tables and so on. We know that this is equal to 2 to the n minus 1. Go look up the formula. Or you can prove this by induction. Okay, that's even a better challenge. Prove by induction that this expression is equal to this expression. Okay. So we have our formula, and by the way, so in n is 4. So if n is 4, then it's 2 to the 4 minus 1. That is 16 minus 1. That was the 15 moves. I go look at the movie and count my actual moves. I must have made a mistake somewhere in my counting. So what was the original problem? Okay. How long this is going to take? Well, h of 64 is 2 to the 64 minus 1. And it can move 1 second. So it would take, this many seconds, after this many seconds, the universe will expire. What is this? Well, it's about more than 500 billion years. So we kind of are safe, okay? And so coming back to our monks, I think our monks have to recruit new monks. They have to find some way here, because they're going to be busy for a while. It's kind of amazing, right? This is 64. Okay, it sounds big, but it's the number of squares on a chessboard. That's not that big, right? Imagine, right? take a chessboard and you put numbers on the chessboard and you use these numbers instead of piles. It's not a big thing. I mean, it's very easily to make. But the game to play takes 500 billion years. That's kind of surprising. Yeah? Okay, I'm going to do one more. No, two more, I think. Yes, two more. But this one I'm going to do a little bit quicker, otherwise the movie, I don't want to make these movies too long. By the way, I'm not going to do the whole thing of this section. We were going to come back to some things later. As I said, we're going to take our time. But the next one is here. So we will count the number of bit strings of length n. Bit strings now, of course, means zeros and ones, right? Of length n with no two consecutive zeros. Now, if you try to say, can I perhaps do this with my previous counting techniques? Think about it, it's not so easy anymore, because where we were counting, you could try to, perhaps, it's a good challenge, but it is much more difficult, right? Because there is each time I make a choice, it depends on, it's not just that I choose the next one, it all depends on when I choose my zeros and when I choose not zeros. Okay, so the way to just resolve this is, by looking at, and this is very often the case, so what we're trying to do is build such a string. So building such a string of length n from previous strings that we have built. Okay, now how does such a string of length n look like? Well, there are really two possibilities. Let's look. So two possibilities, and this is something that is of valid strings. So valid meaning, okay, when we use valid always in this problem, it means satisfying the requirement, no consecutive two zeros. Well, one possibility is so the first probability is that we have, it ends in a 1, okay? And it has no consecutive zeros, so this particular one, so this has now length n minus 1, should not have n, it has to be a valid string as well. Okay, so let's call the number of let's call this number an, and we're trying to find a recursion relation for an. But before I use this previous fact, that's not all possible valid strings, because a valid string can end on a 0, right? If a valid string is on a 0, it can either end in a 1 or in a 0. It's one possibility or the other. But if it ends in a 0, what's the previous digit then? It cannot be a 0 because it's a valid string, and valid strings do not have two consecutive zeros. So this must be a 1. Right? If it ends in a 0, the previous number must be 1, if it's a valid string. So how many are left then? There are only n minus 2 left. So let's count now how many are there. Of the first type, well, it's the as I said, what's in the boxes here, this is a valid string of length n minus 1. So by definition, that is n minus 1 of those. In this box, this is a valid string of length n minus 2. Why n is minus 2? Because the 1 and the 0 already they are fixed now, right? It either ends in 1 or it ends in a 0, but then also must end in 1, 0. So there are only n minus 2 here. Now, what we also have to be careful, so this is an OR, right? 1 OR. And then we know that is the sum rule, but in the sum rule we have to make sure that we don't double count anything. Now, it's clear that case 1 and 2 are exclusive, right? You either end with 1 or 0. So that means that by the sum rule, an is an minus 1 plus an minus 2. Okay, so that leaves us, we have the recurrence relation, but we also always have to be careful that we find what the initial conditions are. So what is A1? Let's think about what A1 is. How many valid strings can I make of length 1 that have no consecutive 0? Well, 1 is 1 and 0 is 1. Okay, so these are the solutions. So these are the solutions, right? So the valid ones. 1 single string, 0. So there are 2 of them. How many are there of length size 2? Why do I need 2 initial conditions? Because I have something that depends on 2 previous values. Okay, we will talk about this more in detail. What kind of initial conditions we'll need when we try to solve such a thing. But so here we need these 2. So A2, what is this? By the way, yes, what the recurrence relation you recognize, right, is the Fibonacci relation. But you see the initial conditions are different. In the Fibonacci, A1 would be 1, but A1 is 2 here. Let's see what A2 is. How do I figure that out? Well, just try all the possibilities. 1, 1 is a good one. 1, 0 is a good one. 0, 1 is a good one. They're different because they're different strings. What about 0, 0? No, that's not a good one. So we have 3 here. So that's the initial condition. So we have the Fibonacci here, but with different initial conditions. Now, I'm not going to solve this because that's something for later, but this is about setting it up. So the last one I'm going to do is, so let's call a valid decimal number if, so a decimal number is valid, let me put it this way, okay. Decimal number is, let's call it valid. So for the purpose, this is only for the purpose of this question, right? Is valid if it has an even number of zeros. Okay. So let's think of how we can make this, okay? Okay, so the one possibility is, so I'm building here my valid string, okay? And the way that I build normally is by adding one more element to the string, okay? So we look at the, and suppose that this is a valid string. So this is a valid string. Oh, sorry, I want to do this way. That's a valid string of length n minus 1, right? And I want to keep it valid. What should I not do? I should not put a 0 there because in n minus 1 there are an even number of zeros. If I put a 0 there, I'm screwing that up. So here I have 9 possibilities. So, okay, 9 possibilities. So here I have to put a number that is not 0, okay, 9 possibilities. Okay, so no, let's not do the counting yet. Okay, let's first figure out what's the second possibility. This, well, okay, why is this not enough? Because there are going to be numbers that end in a 0 and that are valid. So now we have to think about that. So because the first procedure cannot give those numbers, right? The first procedure is going to give me a number that is not 0, like that's what often with a star means, it's a non-zero element. So let me put it like not 0, okay? So 9 possibilities there. But what about, for instance, 1 0 0 1 0 0 is a valid string and it ends in a 0, so it would never be case 1. So I have to consider now strings that end in a 0. Now let's think about that. How can I make a string of length n minus 1 of length n that ends in a 0? What has to happen? What have this to be? This has to be an invalid string, namely having an odd number of zeros, because then adding this extra 0 makes it valid again. So in what I mean here is this has to be invalid. And so again, the size is n minus 1. So let's now count how many are there of type 1. Of type 1 there are, so again, the number, let's call this an of those guys, right? So here, this is an minus 1. This is this many choices, and here I have 9 choices times 9. This is the product rule, okay? So here I'm counting the possibilities. So, and this is just as an example. Now, you understand here what is the product rule? I have an minus 1 possibilities for this one, and I have 9 possibilities with that, and they're independent. So it's the product rule. So, or 9 times a minus 1. What about this one? Well, for this I have only one possibility, so it's times 1 if you want. So we have to count this number. What is this number? Well, it's our invalid strings. What is an invalid string? Well, it's a string that's not valid. How many strings? That's now the, if you want, the difference rule. If you didn't have that, but it comes down to that, right? We count the number of total strings. So you see that our counting principles from previous time really matter now. The number of total strings is what? 10 to the n minus 1, right? And then the number of valid strings is an minus 1. So the number of invalid strings will be the difference. So 10 to the n minus 1 minus an minus 1 times 1, but let's not write this times 1 anymore. That's the formula. You see that? Okay, so again, is there any overlap? No, obviously not, because it really depends on what the last digit is. So the total number an is by the sum rule 9 times an, sorry, 9 times an minus 1 plus 10 to the n minus 1 minus an minus 1. Let's combine the like terms. That is 8 times a to the n minus 1 plus 10 to the n minus 1. Now, this already is much harder to solve, right? What formula? Can we write down a formula for an, not just a recursive relation? And that is what we're going to discuss in the next sections. Okay, I'm going to stop here. There are more examples, but we will do them later.